rod, ROD. And that is the common name that people use for communications. So basically we're saying a rod material is taking or under the axial loading. In this way, we want to study the development of the stress inside material, which is very straightforward. You have already seen in chapter 1. And one more thing we want to study is about the deformation or change in the length of the rod material. We call it deformation. So in this way, in this chapter, we're going to study the equation is how to formulate the deformations, or we call the axial deformation of the rod. For this case, the deformation will be positive because it's stretched. For this, the deformation will be compressed and negative. Okay, so that is our topic. And the concept of the deformation or the stress can be like this. In concept, in chapter 1, we have learned, by the way, in these chapters, the loading is always, for our model setup, is normal to the cross-section. So which means in chapter 2, actually we're going to study, our focus is the normal stress. Okay, and in chapter 1, we know the stress is force divided by A. A is the cross-sectional area. Really doesn't matter the cross-sectional area. For example, if this is 2P divided by 2A, then that is the same magnitude like this case. As long as the this formula we call the strength. By definition, strength is defined by the deformation. Deformation is the change in the length, and divided by original length. Come on in.
I think there's one more chair over here.
There's one more chair here, good chair, and try to squeeze in the space if you wish. Okay, that is the definition for the strength. And actually, in specific, this is called the normal strength. Because in this chapter, we talk about is the normal loading induce the normal deformation. So, and use the symbol is, we call the epsilon. And epsilon is for the normal strength. By definition is deformation, we use delta. So change in the dimension is used delta. The original length, for whatever original length, we simply is L. That would be the new equations, and that equation is pretty much simplified. And again, this is the average sense like we have before. In chapter 1, we have known that the force divided by A, that is the average. We know in chapter 1, in this class, we only focus on this is the average sense or the approximation of the stress. We don't consider stress concentration. The same thing, we won't consider the large deformation due to the local stress concentration. That won't be the issue we're going to consider here. So again, if you wish, actually here we look at is in the average sense, okay? But we don't have to emphasize, but you just keep in mind. And with the deformations of the stress and with the definition of the strain, we are going to try to find the relation between the two quantities. The relation between the stress and the strain actually is one of the material properties. And how to identify or how to test out the material properties. And that is what we mention is we call the uniaxial tension testing. Uniaxial tension testing is this. We prepare a specimen, a sample, pretty much it's like the rod. And we have to carefully follow some standard, ASME standard, to well define the diameters and the lengths. We make sure that everything here is uniform as possible. And then we kind of screw it on the two sides, and then we insert into the machine, and the machine basically is kind of gradually apply the force, try to elongate and break the material. Okay, and the process is very slow. It's very slow, and we call this this process is called the quasi-static. Quasi-static. Okay, so basically the loading is applied very slowly, and then we record the corresponding information. For example, we're recording what is the stress in between the 2 points, as well as what is the deformation, the change in the length between the 2 points. So the machine will be able to do it automatically. And the setup is pretty much like this. Then what information we record? Actually, once we finish the process, then we will get a curve. Something like this. This is for ductile material. This is for many brittle material. And ductile or brittle is like this. Ductile material, just like, I try to use the very extreme, try to exaggerate, yes.
I just got a quick question about the
Yeah.
deformation. Is that the distance, perhaps like the difference in length plus the original length, or no?
Yes.
It's plus the original length.
His question is this. Here, his question is concerned about this. And here we use the original length, but we know that during the deformation, the length is changing over time. So that is his question. In this class, and again, we try to focus on the basic concept, but sustaining using the calculation as simple as possible. Okay, so basically here we always divide by original length.
I mean, like for deformation, like let's just say it stretched like 2 millimeters.
Yes.
So would we plus that to the original length, or no? Would it just be 2 millimeters?
Just for example, if the material model is like this,
okay.
and then after the loading, we apply the loading like this, and then this material will be deformed from original to here. And then this is our deformation here, from here to here.
Okay, perfect.
And this is our original length. And let me call it L0. So by our definition, this is delta simply divided by L0, that's it. Not taking delta divided by the after the deformed length, no. We just take as the simple definition. This is for ductile material. Ductile material just like rubber, and which is very flexible, stretchable. Compared to the brittle material, just like the brittle material, if we have a chalk, traditional here is a chalk. Chalk is very, very brittle. Okay, so those are the two basic kinds of the material. So the loading will record whatever the vertical axis is for stress. The horizontal axis is for strain. So the computers will record those information during the process, the loading process. And quasi-static is the loading is increased, the force is increased gradually, very slowly, try to avoid any dynamic effects. Okay. So that process, we will record the curve like this. And in particular, those curves, we have two basic regions. The one is this. In a very narrow region here, most of the time we will notice the curve is actually a straight line. Okay, and actually it's a straight line in a very narrow range. Beyond that case, beyond that range, then will become the nonlinear and curve. And in our ES 331, this narrow range is our focus. We call it elastic range. In this narrow range, actually is this. An object is deformed, if that was deformed in an elastic range, then once the loading is released, this model will be able to recover back to his original shape. And in this elastic range, there's no permanent deformation will be caused in this material. And that is our focus of ESD31, and we call it elasticity. Okay. And beyond that range, there's a huge range, and that means once we remove the loading during the loading process, the material will try to recover. However, will recover back to a portion of original length because the material will suffer the permanent deformation. So once the material be loaded up into the plastic domain, then once we release the total loading, the material will be deformed permanently. And that is called the plastic deformation. The plastic deformation actually will further classify into the few ranges, but this one, there's another story, we don't need to focus on this. So in this elastic domain, I can characterize, draw the figures like this. This is a strain, this is stress. And computer will record the curve will pretty much like this. And this is a straight line. A straight line, basically that has the slope. We can categorize with the slope. And this straight line is in elastic domain. And this one slope we define as a E. All the textbooks, all the people in this field, they use E. That is the only symbol we use. Basically, in this way, we found the relation in the elastic domain is sigma equal to E times epsilon, because this is a straight line. And E is, we call the Young's modulus. Different materials has a different Young's modulus, and the Young's modulus can be obtained by performing the uniaxial testing. The uniaxial testing can be either stretching or can be compression. And some material will exist the different Young's modulus in stretching or compression, but most of the material we can just simply use the same number for stretching or compression the same. This relation is called Hooke's law. So people would ask you what you learned in mechanics material. You simply reply two words, Hooke's law. We learn Hooke's law. We apply Hooke's law to different loading conditions. And this is the first condition you're going to learn. Okay. So under this case, we can further plug into our situations. Hooke's law, right now we learn is sigma equal to E times epsilon. What is sigma from our loading case? For example, if this is our material model and under loading P, and this material, for example, right now we know that it has Young's modulus E, and it has, for example, this is uniform material, it has a uniform cross sections. Doesn't matter if it's rectangular or circular, as long as it's uniform cross section. Let me call the cross sectional area of this is A, and and the length is L. So under this case, you can see the stress equal to P divided by A. The strain, we know that under this situation, they will get elongated, and let me call this is delta. elongation or deformation is called delta. So strength equal to delta divided by original length, L. And we simply apply Hooke's law to the relation here. Everything in this equation is algebraic information. There's this is the algebraic equation. It's not differential equation. So this equation is very straightforward to apply. And most of the time, the people like to rearrange this equation into this. Delta equal to PL over EA. That is the only equation in chapter 2. Yes?
What is E one more time?
E is Young's modulus.
Okay.
And how to determine E? Then we simply use the testing. We found the curve, and then we simply approximate the slope by E. Not to approximate, to measure the slope by E. Any other questions? So in this equation, how many numbers were given? Suppose we are given the geometry, which is dimension L. If we know the geometry, then we can predict or we can calculate, or we are given the cross-sectional area. And E is the material properties. Once you determine the materials like aluminum or steel, then the E is the material properties. You can check it out from the data book.
So it's just a constant?
Constant. So most of the time, those things will be the constant. So depends on the magnitude of the loading, then you can calculate the corresponding deformation. If the loading is negative, this should be corresponding gets shortened negative. Okay, so that is very straightforward to apply. Any questions about that equation? That is the only equation I can tell you. That's the only equation. That's the only important equations. Before we move on to the next page, another keyword, another terminology I want to mention to you is the sigma y. In both figures, we label as a sigma y. And what is sigma y? Beyond this threshold, the material actually is getting into the nonlinear curve or the nonlinear domain or plastic domain. So sigma y is the kind of threshold or the edge to tell us if we load the material such that its maximum stress is over this threshold, then this material is very likely get into the plastic deformation range. So the people would ask, so how to use the sigma y? Sigma y is a threshold. If you want this material be loaded in the elastic domain, you make sure the material shouldn't be loaded up exceeding this number. And this one, sigma y, is called the yielding strength. Sigma y is called the yielding strength. And I don't know why the people using these strengths, actually sigma y is one kind of the stress. But the people just call it strength, yielding strength. And barely people use the yielding stress. I don't know why, but you better use the right word, and otherwise you will get laughed by people. Okay, really that is, I don't know why they call it yielding strength, but really it is a stress. So sigma y has the same unit as a stress. And again, this is a material properties. Different material have a different capacity to endure within the elastic domain. The higher the yielding strength, then the larger the material can be loaded up still within this elastic deformation. Okay. So that is the second word, and we can move on. And this is simply the material characteristic for the fractal material, ductile and brittle material. The brittle material simply is this. The brittle